Here's another example. We're going to find the centroid of the solid enclosed by the cylinder. X squared plus y squared is 4. So this is centered at the origin, and you can see it in the xy plane. We have a circle of radius 4. There's no limitations on z, so the cylinder just keeps going up. And here we have our top circle here. It is bounded above by the paraboloid z is equal to x squared plus y squared. And that is what we're getting here, where we have these circles that are increasing in radius as z increases in height, and bounded below by the xy plane. So here's our xy plane. So the area or the volume that we're talking about is this sort of light green, and this dark area inside here is the inside, so it's hollow, okay? So what we're talking about here is just this volume created by this base and the sides of the cylinder, a circular base, and then the sort of like angular paraboloid which sort of cuts into it. So if we want to write x squared plus y squared equals 4 as a cylindrical equation, we know that x squared plus y squared is r, and so we can just say that r is equal to 4. And then if we want to write the next equation, oops, there we go, we know that z is equal to x squared plus y squared again. X squared plus y squared is r, so we say that z is equal to r. So the solid centroid lies on its x-axis, on its axis of symmetry, and you can see that it's symmetrical above the z-axis, which make x bar and y bar equal to 0. Okay, these are our coordinates for our centroid. So our centroid coordinates for the x and y will be right at the origin. So to find z bar, which is the z coordinate for our centroid, we must divide the first moment by the mass. So let's start by finding the moment. And we want to integrate this volume. So let's think about our limits of integration. So we're going to do, this is a triple integration over the volume with respect to z. So our integrand, we have got a z there, dz, and then r dr d theta. Let me just mark this because this section gives us our volume, and then the z gives us our moment. So with respect to z, let's look at that. We want to think in terms of z, and z will start at 0. Let me change that pointer. Okay, z will start at 0 and it move all the way up to a height of r squared. And I'm going to color code this. We'll start with blue. So z has a max height of r squared, so z is going to go from 0 to r squared. Now we want to integrate with respect to r. And I'm going to use red now. So our radius starts at 0 and reaches out to the edge of this circle. And we know that r has a max of 2 because that's the radius of this circle. X squared plus y squared is r squared, 4. So our r limits of integration will go from 0 to 2. And the last integral of limits of integration are for theta, and theta would start here and wrap all the way around a complete 360, right? So our limits of integration for theta, we go from 0 to 2 pi, right? Because we go all the way around to 2. starting at 0 and ending at 2 pi. Okay, so let's start our integration. And we'll have the 0 to 2 pi and 0 to 2. And we'll integrate with respect to z, and we get z squared over 2 from 0 to r squared. And don't forget the r, dr d theta. And this has us go from 0 to 2 pi. Again, 0 to 2. And if we integrate z squared over 2 from r squared to 0, this gives us 1/2, we'll put the 1/2 out here, times r squared squared, because this is z squared, z is r squared, we're squaring that. So that's r to the 4th times r. So let's make it r to the 5th, dr d theta. And so now, let's see, right, the outer integral, 0 to 2 pi. The antiderivative of r to the 5th is r to the 6 over 6, and we're evaluating that r from 0 to 2. Of course, we've got our d theta here. And this gives us 1/2 times 1/6, so that's 1/12, times the integral from 0 to 2 pi. And evaluating r to the 6 from 2 to 0 is 2 to the 6 d theta, which gives us 2 to the 6 over 12 times theta evaluated from 0 to 2 pi, which is going to be, well, let's take 2 to the 6, and we'll do a little canceling here. If I can cut the 12 in half, and I get 6, right? Which means I can factor out a 2 and get 2 to the 5th. And then I can cut the 6 in half and get a 3 and factor out a 2 and get 2 to the 4th. So I end up with a coefficient of 2 to the 4th. 2 times 2 is 4, times 2 is 8, times 2 is 16. So this gives us a 16 times 2 pi minus 0, or just 2 pi. And we have a 3 in the denominator. Let's not forget that. And so this works out to be 32 pi over 3. I'm going to circle this. This is sort of an intermediate solution. This is giving us our moment, because now we need to find our mass. And our mass is going to have the same limits of integration, 0 to 2 pi, 0 to 2, 0 to r squared. And our integrand will be just dz r dr d theta. So we integrate from 0 to 2 pi, 0 to 2. And our antiderivative is just z here, evaluated from 0 to r squared. And then we have r dr d theta. A lot of writing here, 0 to 2. Okay, so our z is r squared, so it's just r squared times r is r cubed, dr d theta. And so now we're going to work out the antiderivative with respect to r, and we get r to the 4th over 4 evaluated from 0 to 2. And then we end with d theta. And if we factor this out, we have 2 to the 4th, right? So I can say 2 to the 4th over 4 times the integral from 0 to 2 pi of d theta. And of course, 2 to the 4 over 4 is going to give us 16 over 4, which is 4. And then our antiderivative is theta, evaluated from 0 to 2 pi. So this gives us 4 times 2 pi, which is 8 pi. Let's circle our intermediate solution for our mass. Again, this is our mass, and this is our moment with respect to the xy plane. So to find the z coordinate for our centroid, it is the moment over the mass, where the moment is 32 pi over 3, and we're dividing by the reciprocal, by the mass, which means multiplying by the reciprocal, 8 pi. And of course, the pi's will cancel out. Matter of fact, the 8 cancels out, so 8 goes into 8 once. Oops, I crossed the wrong one. And 8 goes into 32 4 times. So we end up with 4/3. So the coordinates for our centroid are sort of x bar, y bar, z bar, which is 0, 0, 4/3. And this we can box. This is our final answer for our centroid, for our solid.